So here we're talking about another characterization of trees. That's not in the book actually. So it says the following: a connected graph is a tree if and only if all its edges are bridges. And this is actually very easy if we just look at the two definitions of a bridge and a tree and maybe use theorem 4.1. Let's write them all out. So here are the ingredients that we're going to use to prove this statement. We're looking at the definitions. So tree is a connected graph without cycles. A bridge in a graph is an edge whose removal increases the number of components. So here we're talking about connected graphs. So that means if we remove a bridge, then afterwards we have more than one component. Actually, we have two components. It's disconnected afterwards. But we'll not, in our proof, we're actually not going to use this definition here, the second one, but we're going to use theorem 4.1 instead, in which it's proved that a bridge is exactly an edge that does not lie on a cycle. Every edge that does not lie on a cycle is a bridge. That's theorem 4.1. So we're going to use the definition tree, and we're going to use this theorem, which gives us a new definition for bridge. And if we put these two guys together, let's read our statement again. A connected graph is a tree if and only if all its edges are bridges. So let's look at one direction. If all the edges of a connected graph are bridges, that means no edge lies on a cycle. That means there is no cycle. Oh, a connected graph without cycles is a tree. So if all its edges are bridges, then we have a tree. On the other hand, if we have a tree without cycles, if we have a tree, then we have a graph without cycles. Well, that means that no edge lies on a cycle because, well, we don't have any cycles. So every edge in my graph is a bridge. So that's the whole proof.